Hi guys, here we have lesson 2.4 on the normal force. So this lesson is all about knowing the difference between the force of gravity and something that we call the normal force. So for the first question here, we're going to review what weight is. So remember, your weight is essentially the force of gravity. So a lot of times what we'll do, instead of writing the W with the vector arrow that you see there, we'll write Fg. Now, Newton's first law says that any force is equal to mass times acceleration. And when it comes to weight, the acceleration that we're talking about is acceleration due to gravity. So this first formula, it's essentially F equals ma. So if we rewrite it, we can write the same formula as force of gravity is equal to mass times acceleration, and acceleration can be acceleration due to gravity. So my preference, instead of doing the W for weight, is to do the Fg, and that's what you'll see me doing in later lessons. First example, what's the weight of a person of mass 60 kilograms? Assume that that person is on Earth. So the weight, or the force due to gravity, is equal to mass times acceleration. Their mass is 60 kilograms. Remember, the mass of an object is how much matter makes up that object. The mass will never change. So this person could go to the moon and their mass will always be 60 kilograms. It doesn't matter where they are. But their weight, or the force of gravity, is going to be different here on the Earth, where acceleration due to gravity is negative 9.81, than it would be on the moon, where the acceleration due to gravity is smaller. So multiply these together, and I'm going to get 5.9 times 10 to the 2 newtons. Now, what is the normal force that we're learning about here? We're going to have a look at just a box sitting on a table or the ground or different spots and take a look at what we would call the normal force. So Newton's third law states that every action force has an equal and opposite reaction force. So what exactly is counteracting gravity? So this box sitting on the table that you see, it's not falling through the table. So there must be some force that's keeping this box from following gravity and being dragged down. This is called the normal force. So the normal force is basically, from Newton's third law, a counteracting force to gravity. So this formula can be used in some circumstances to say that the normal force is just the exact opposite, so a negative sign, of the force of gravity. Now this only works on flat surfaces. When we start talking about angled surfaces, you'll see that there's a little bit of a tweak that we have to make with force normal. So the normal force is equal in magnitude but opposite in direction to the force of gravity. It occurs when an object is coming into contact with any surface. So it's the reason why the box is not falling through the table, because there's a force keeping the box up. Now this part's very important. The normal force acts perpendicularly to the surface that the object is on. So in our first example with that box sitting on the table was a direct horizontal table, and the normal force was acting perpendicular or at a 90-degree angle to that table. So if you want to see that drawn out, there's your 90-degree angle to the perpendicular table there. So let's draw some free body diagrams for the following scenarios and take a look at where the normal force would be. So if we just draw a horizontal line and we've got our little box, what are all the forces acting on this box? Well, force gravity is always going to be acting, we say down, but really we mean towards the center of the planet. Okay. Now you have to figure out what your surface is looking like, and you have to draw your normal force perpendicular to that surface. So if we have a horizontal surface like this, perpendicular would come like this at a 90-degree angle to that surface. So this is the example where force normal and force gravity do happen to act in the same direction, just opposites. On a ramp, this is where you can really start doing some really exciting physics and math work with angles, but we've decided during this emergency remote learning that we're undertaking for the pandemic, we are going to cut this. I will show you what it looks like, because ramps really bring in a lot of applications of what we're talking about. So here's a ramp and here's a box sitting on the ramp. Now gravity acts towards the center of, let's say, the Earth, no matter what. That's how gravity is always going to act. So for this one, force gravity still pointing down or towards the center of the Earth. However, force normal is always perpendicular to the surface. So since you can see that the surface is slanted like this, the normal force has to actually come off at an angle like this. Now, what's keeping this box from sliding down the ramp? Well, we're going to learn later about a force of friction that's keeping it from sliding down the ramp. And what we aren't covering, but some of you may be interested in learning more, is that this force gravity can be broken into these vectors. Okay, now these make a 90-degree triangle, so you can do things like SOHCAHTOA with those vectors, and you can start adding vectors that match vertically, and I say vertically in quotations there, and horizontally as compared to the actual ramp itself. So again, this is something that we'll be omitting, but if you are interested, you can let me know. I can point you in the direction of more information. The big thing to know on that one is just that the normal force is always perpendicular to the surface. It's not simply the opposite of gravity in that case. On a vertical line, so a wall, if you've got this box and it's being held against this wall, we have a lot of forces at play here. First one to put on is force gravity. That one's pretty simple. Okay. Now the tendency is students want to put normal force now pointing up, but that's not correct. The normal force is always perpendicular to the surface. So the surface being vertical means the normal force will be horizontal in this case. So what would keep an object like this from sliding down the wall? Well, there might also be some kind of applied force pushing it into the wall. Like I might be holding this box against the wall and applying a force, and there might be a normal force acting in the other horizontal direction. What might keep this box, if I'm holding it against the wall, from sliding down the wall? You might have guessed that's the force friction that we're going to learn about later. Now for a table, this is not a trick question. If I go back to part A here and I just put some legs on this horizontal surface, that's now a table. This is exactly the same free body diagram. Because it's raised off the ground, it doesn't change anything about what you're going to write there. So this exact picture is going to be what it would look like if you have your free body diagram on a table now. All right, so those previous examples, we were assuming that the box was not moving, so all of the forces would have a net of 0, so no acceleration for those boxes. Another way to say that, net force acting on the box being 0, so Newton's first law, F equals ma, the force, or pardon me, Newton's second law, F equals ma, the force being 0 means the acceleration would be 0, so the box was not moving. The net force, when we see this word net, we've already done examples of this, but net just means add them all up. One way that we say that in math is we call that the sum. So we're taking the sum of all forces acting on that object. And we do the net force in the horizontal and the vertical direction separately. Consider a box on a line, as we have drawn, being acted upon by two forces. Force 1 is 35 newtons, force 2 is 20 newtons. What is the net force? So you can see these arrows are both pointing towards the right. So what we have here is we have a net force, and I'm going to put in the x direction for this. You could put horizontal as well. A net force in the x direction is going to be the sum of F1 and F2. Now, I'm going to say that since those arrows are pointing to the right, that both of these forces are in the positive direction. So we have a net force in the x direction of 35 newtons plus 20, or 55 newtons, and that positive just meant to the right. So you would see that this box is accelerating to the right. What could be happening here in words is this box could be pushed by person 1 here, and this person here could be pulling the box. And the box could represent any kind of object. Now, what's not drawn on this is the fact that there is a net force in the vertical direction, but it just happens to be 0. So we haven't drawn it because it doesn't affect the question. So what's really happening to this box is there's a force of gravity acting on it and a normal force perpendicular to the surface. If I wanted to do the net force vertically, I would have to add up force of gravity plus normal force. And what we know is that the force of gravity is just the opposite direction of normal force. So it would look something like this. If you take force normal and you subtract force normal, you get 0 newtons. So those are something, if they cancel out like that, you usually won't see them drawn on the free body diagram. We just simplify it so that we can take a look at the forces that are really making the object move. The next one has these forces now acting against each other. So you can see the arrows, one is pointing right and one is pointing left. So what do we need to do in this one? Well, we need to make sure that we give these the proper signs. So I'm just going to do the net force, again, in the x direction. It's still going to be F1 plus F2. But in this case, F1 is going right, so that's the positive direction, and F2 is pointing left, so the negative direction. This might be like somebody pushing the box this way and somebody pushes it the other way, for example. So force 1 is in the positive direction, positive 35 newtons, and I'm still adding, always adding, but in this case we've got the negative direction for the 20 Newton force. If you add these up, you get an answer of positive 15 newtons, really meaning that there's a 15 Newton force acting right, so in that direction. So this box is going to accelerate to the right. Forces can act in more than one dimension, and this is where angles will come into play. So for this one, we have Amanda and Kirsty pulling a cart. Amanda pulls with 25 newtons due east, and Kirsty pulls with 15 newtons at 30 degrees north of east. What is the total force on the cart? So, free body diagram, doesn't matter what the object is, just draw a rectangular box like this with a dot in the middle to represent the cart. Amanda pulls with 25 newtons due east. So this is Amanda, 25 newtons due east. And Kirsty pulls with 15 newtons, so a slightly shorter vector arrow, 30 degrees north of east. So if I look at my east line and I go towards north, that right there is 30 degrees. What do we do with that 30 degrees? Let me draw it again. 15 newtons. It's going to have an x component and a y component. And you can quickly do your SOHCAHTOA to figure out the force in the y and the force in the x. Very similar to what we did in Unit 1. So we're going to have sine 30 equals opposite over hypotenuse, and cos 30 equals adjacent over hypotenuse. So I'm going to use these in my future calculations. What I have is I have an x direction vector and another x direction that I need to add together. So F net, the sum of all of the forces in the x direction, is we've got 25 newtons east, so that would be a positive. And we've got Fx here being 15 times cos 30, also acting in the positive direction. So here we go. We're going to add those together and just leave that answer in our calculators so that we can use all of the decimals in future calculations. And I'm getting an F net in the x direction to be 38 newtons, but of course we have all those decimals as well. F net in the y direction is next. We see that the green vector is strictly in the x direction. There is no y component to that one. So the only y component that we get is Fy up here. It's pointing up, so it's positive, and it's 15 times sine 30, or about 7.5 newtons. Now, what do we do when we have an x component and a y component? We draw a new diagram with an x and a y. We give it a resultant and an angle, and we solve for our overall net force. So in the x direction, I had the 38. Y direction was 7.5. We're going to do Pythagorean theorem and a tan ratio. So you can pause the video at any time so that you can put this in your calculator. I end up getting 11 degrees for my angle, and that is pointing north of east. And for Pythagorean theorem, to get F net, I'm going to take the square root of both sides squared and added together, and I get 39 newtons. So I'm just going to pop my angle after that. And that is the final force that's applied to this cart that's being pulled by two people in two different directions. So if this cart was to accelerate, that's the direction that it would accelerate, which is exactly what we have happening in part B. If the cart has a mass of 65 kilograms now, what is the acceleration of the cart? We want to reference Newton's laws whenever we can so that we're using them. So this is going to be by Newton's second law. And recall that Newton's second law is F equals ma. What do we have for a force in this question? Well, we had two forces being applied. We added all of the components in the x and y direction together, and we got an overall net force. Mass we're given, and acceleration we're looking for. So I'm going to put my net force in there. We got 39 newtons. 65 kilograms is the mass, and we want acceleration. A little algebra, divide both sides by 65 kilograms, and we'll get an acceleration there of 0.60 meters per second squared. Now, acceleration has a vector arrow over top of it. So because of that vector arrow, I'm going to write my answer meters per second squared with the same angle I just found in the previous question. Now, I'd like to take one moment to analyze what we call our fundamental units here. So for this question, we ended up taking newtons and dividing by kilograms, and we got meters per second squared. So that really doesn't make much sense. We don't see that anything is canceling there. So to analyze the fundamental units, we need to write everything with our base units that we always use in physics. So that's things like meters, seconds, and kilograms. If we can write everything with those units, then we can actually see them canceling. So what I actually want to write with fundamental units is what a newton is equal to. So force is something that we measure in newtons because the units of force are actually quite messy looking. So think about what this would be. This would be mass and acceleration. So mass is kilograms, and acceleration is meters per second squared. These are two fractions multiplying. There's a secret denominator of 1 under the kilogram. So I would go top times top, bottom times bottom, and I get that a newton is actually a kilogram times meter per second squared. You can see that's quite a mouthful, and that's exactly why we call it a newton, so that we don't have to write that every time. Now I'd like you to pause the video and show why in the example above, when we took newtons and divided by kilograms, were we able to get the units for acceleration. So pause the video and try that with the fundamental units, and I'll meet you back here. Here I go, subbing in the fundamental units for kilograms, or pardon me, for newtons. Kilogram meters per second squared, that's what a newton is. And we were in this question dividing by kilograms. So yes, the kilograms cancel, but when you have fractions within fractions, it can be difficult for you to know when things can actually cancel. The way that I would solve this is I would actually write the top divided by the bottom. Then I would use my fraction rules. When I'm dividing by a fraction, I change it to multiplication and I flip this fraction. This is why the kilograms can cancel. You now have the multiplication of two fractions, so any top can cancel with any bottom, just like we did in our rationals unit in Math 20-1. The kilograms cancel, and on the top we have meters times 1, and on the bottom we have seconds squared. So analyzing these units can show that you have quite a deep understanding of what's going on in these questions. So what we have for practice is a worksheet and answer key posted. I would be happy to go through any questions that you have via email, or I would also love to see your faces and set up a video chat. Let me know.